Now that we are comfortable with determining the complexity of link state and distance vector routing protocols, which work for flat or mesh topologies, we understand that in real world, the networks are not pure mesh or not absolutely flat. Instead, we find hierarchical networks, which we see in our ISPs worldwide. Why is that? In this module, first, we'll understand why do we need hierarchical routing protocols, and then we'll talk about their implementation methodology. The variation in the implementation methodology eventually determines the complexity. Two primary references are there for you to look up further information for hierarchical routing protocols complexity. First, the textbook by Kuros and Ross. Second, the work you can Google by Leonard Kleinrock and Professor Farooq Kamoon. In 70s, they worked on hierarchical routing protocols and they also established very insightful relationships for their complexity. Hierarchical routing protocol is necessitated by the fact that all the routers that we see around are not exactly equal. They vary in their connectivity, bandwidth availability, the resource, and hence the cost. The problem is exacerbated by the fact that these routers, if they are connected in an all mesh environment, would result into taking very large routing tables that would become unmanageable. So a natural solution that comes into mind is to form the position and level of every router depending upon its location, the number of networks it is connected to, or the number of hosts that it is directly connected to. The methodology to realize the routing protocols in a hierarchical manner come in a very intuitive way. First, we aggregate all these routers into a single administrative domain called an autonomous system. Each autonomous system belongs to at least an ISP. However, an ISP could have more than one autonomous system as well. Within an autonomous system, the routers which belong to that autonomous system run the same routing protocol. It is called intra-autonomous system routing protocol. However, since these autonomous systems have to be connected to each other to form the global network, so when they connect to each other, they must establish a relationship between them through a device called gateway. A gateway essentially sits between two autonomous systems, speaks two different languages. By languages, I imply that a gateway runs the routing protocols for the autonomous systems to which it is connected. For instance, if in one autonomous system, RIP as a routing protocol is being used, in another autonomous system, EIGRP could be alternatively used. Let's look at it through an example scenario. Here we see that we have three autonomous systems. Autonomous system 1 has a router called 1D. The inner operation and details of 1D are shown to you here. We see here that the router in autonomous system 1 is running two routing protocols, the intra-autonomous system and inter-autonomous system routing protocols. Together, these create the forwarding table. The forwarding table contains entries for internal destinations as well as for external destinations. Now that we have an idea into how hierarchical algorithms and protocols work, let's look at a complex situation in which we have a hierarchy of multiple levels of router clustering. Here you can see that we have the router which forms the zero level cluster. This router forms a group with other routers in a hierarchy called level 1 cluster. Level 1 cluster form another hierarchy together in level 2 cluster, and subsequently we see a level 3 cluster all around the global network. Here, although it looks fairly easy to manage in terms of administration, operation, and maintenance, however, if we were to look inside the details of every router, we'll appreciate that together the interplay of these routers creates fairly complex routing tables. For instance, if we refer to the same figure that we have just seen, on the y-axis we have the destinations marked as 1.1.1 to 1.1.4. These belong to the same cluster. Now, if the clusters within the same supercluster are represented in the routing table as 1.1, 1.2, and 1.3, and then the superclusters are also enumerated as 1, 2, and 3. On the x-axis, we could represent their associated information. For instance, what is going to be the next node, how much delay is expected, and how many hops are required. With this, we see that the overall management of such a large and complex routing table requires a fine interplay and operation of intra and inter-autonomous system routing protocols.